Lesson 19 is modeling the trig functions, and in 19.1 we're going to be kind of translating verbal descriptions of trig functions into actual functions themselves. So before we get into the examples, I want to review what the parent functions look like for sine and cosine, and then we have kind of a few tips to help with this section. So for sine, the parent function is just y equals sine of x, and the midline for both of these functions is going to be at y equals 0. I'm just going to draw that in here. Both of their amplitudes will be 1. Really, the main difference between the two is kind of where they're starting at. So sine starts at the midline, and then it goes up to its maximum. It comes back down to the midline, and then it goes down to a minimum, and then it goes back up to the midline like that. So sine starts and ends at the midline. And then we'll continue in both directions forever. For cosine starts at its maximum, so the highest point on the graph. It goes down to the midline, then goes down to a minimum, back up to the midline, and then back up to a maximum to start the next cycle. So they share the same points. It's really just a matter of where are they beginning, where is their initial value or their y-intercept at. So sine, again, starting at the midline, going up first, and then coming back down to the midline. So starting right here, going up, coming down, coming back up to the midline. That's one cycle. And then cosine is starting at its highest point, it goes down, comes back up to its highest point before beginning another cycle. So each of those are just one cycle of each one, sine or cosine. The period of each of the parent functions is 2 pi, and then the frequency is 1 since there's one cycle from 0 to 2 pi. Okay, so here's some tips for solving not just frequency problems, but a lot of these modeling problems. So the first one is just kind of a review of the general form and how to kind of locate frequency in there. So frequency, in the general form, we use b to represent it, which ends up being the coefficient of x. If you don't see a number there, then the frequency would be 1. Number 2 is just a kind of quick refresher on what frequency is. So the frequency is the number of cycles completed between 0 and 2 pi. How many times does the pattern repeat itself? 3. When you're given the period and you need the frequency, you can use frequency equals 2 pi over the period. And then 4, sine and cosine functions, they each have 2 x-intercepts per cycle. So I'm going to use the parent function to kind of demonstrate this. For cosine, I think it's pretty clear. There is 1, 2 x-intercepts crosses the x-axis in 2 places per that one cycle. On sine, it kind of looks like there's 1, 2, 3, but really there's also just 2 for sine as well. It's not like a typo or anything. So there's 1, 2 for sine, and then this one over here that kind of looks like a third one is actually the start of the next cycle, so it's counted in that second cycle. So we just count those first 2 for sine, and then the third one would be the start of the next cycle. So example 1, a sine wave has a period of pi over 8. How many x-intercepts does this function have over the interval? So in order to figure out how many x-intercepts there are, we really have to figure out how many cycles there are over that interval, and how many cycles there are over the interval 0 to 2 pi is the frequency. That's the definition of frequency right here. So frequency is the number of cycles completed between 0 and 2 pi. So for this kind of setup, we'll use number 3, that tip up there where it says when you're given the period, which we are, you can find the frequency by 2 pi divided by the period. So we'll say the frequency, I'm just going to use f, equals 2 pi over the period, which is pi over 8. And then we'll simplify. I'm going to write it out horizontally. So 2 pi divided by pi over 8. And then I'm going to change that instead of dividing to multiply by the reciprocal. So it'd be 2 pi. And then instead of division, multiplication. And then flip pi over 8 into its reciprocal. So it'd be 8 over pi. And then from there we can cross cancel the pi's because 1 is in the numerator and 1 is in the denominator. And we're just left with 2 times 8. So 2 times 8 is 16. So our frequency is 16. So what that means is we get our frequency is 16. So that means over the interval, 0 to 2 pi. This isn't going to be a graph. It's just kind of trying to make it a little bit more visual. So if the frequency is 16, that means that over that interval from 0 to 2 pi, that means that there's 16 cycles. So kind of 16 waves, like copycat waves of themselves. And then tip number 4 up here, it says sine and cosine functions have 2 x-intercepts per cycle. So if it's 2 per cycle and there's 16 cycles over this interval, then we have to do 16 times 2 to get the total number of x-intercepts, which is 32, so 32 x-intercepts. Okay, and then I'm just going to add really quick, so it ends up being, oops, not what I meant to do. It ends up being 32 x-intercepts, but I'm just going to add a little bit more detail as far as like the setup of how we got this. So the 16 was the frequency. And there's that formula for frequency right up here, once given the period. And then the 2, that number won't change. The 2 is the 2 x-intercepts per cycle. So I'm going to say always 2 x-intercepts per cycle. Okay, so when given the period and asked for the x-intercepts, you have to find the frequency and then multiply the frequency by 2. Okay, example 2, write an equation that could represent a sine function with a period of pi. So when we're writing functions, we use either one of these, depending on if it's sine or cosine. So we're going to use, this is sine, so we use y equals a sine of bx and then plus k. So when we're writing functions, we have to identify, okay, like what piece of information is going in for which letter into general form. So in this case, we're given that the period is pi, but we don't have a letter in general form for period, but we have one for frequency, which is, it's b, and we know that period and frequency are related, and we can kind of use this formula to go between the two. So if we're given the period, we have to use that formula to find the frequency, and then the frequency is what actually goes into our equation. So I'm going to move this over. So we want to find our frequency. I'm going to say f for frequency equals 2 pi over the period, which is just pi right there. So 2 pi over pi. Anything divided by itself cancels out, so pi and pi cancel each other out, and then we're just left with that 2. So that 2 is the frequency, and that's what goes in for b, because b is the frequency. And then the rest of the equation can be as complicated or simple as you want it. The only thing that has to be true to properly answer this question is that b is 2. So it'll be y equals, I'm just going to leave a off and leave it as 1. So y equals sine. B is 2, so 2x. And then k, I'm just going to leave as 0, so I'm not going to write that in. The way a lot of these problems will look like in Canvas are you'll be given a list of functions and you'd have to identify all the functions that fall under this criteria. So what that means is we just really have to, we narrowed it down to the frequency is 2. So you would have to identify all of the functions that have a frequency of 2 in them, and then those would all be your choices. The amplitude A can vary and the midline can vary, but frequency must be 2. Moving on to example 3, it says write an equation that could represent a cosine wave with a height of 10. So if it's cosine, I'm just going to start by copying down the general form for cosine, which is y equals a times cosine of bx plus k. And I think it's important to kind of start with, okay, identifying what letter we need to find here, what letter is even related to the height. So I'm going to start off just by drawing a Moving on to example 3, it says write an equation that could represent a cosine wave with a height of 10. So it's giving us cosine, so I'm just going to go ahead and start with writing the formula for the general form for cosine. So it's y equals a times cosine of bx and then plus k. And then I'm also just going to draw a little sketch of a cosine graph. So cosine starts at its highest point, it goes down to its lowest point, and then it comes back up. This is one cycle of cosine. And when it's saying that the wave has a height, saying the wave itself, like from the top of the wave to the bottom of the wave, has a height of 10. So now we want to figure out, okay, what letter in the general form is at least somewhat related to the height of the graph. So we know that b is the frequency, which is how how often the cycle repeats itself from 0 to 2 pi. So that's irrelevant. We don't need that. I'm not going to worry about that. The midline k does kind of have to do with the height of the graph, but that's really talking about like what the height is on a coordinate plane, like kind of the points and stuff. But it doesn't actually have any impact on like the distance from the maximum to the minimum of the graph, like kind of how our sketch is set up. So we're not going to worry about the midline. The letter that kind of at least is related to the height of the wave or the distance between the highest point and the lowest point, that's the A, amplitude. And amplitude, like kind of the definition of it is the distance from the midline up to the maximum or down to the minimum. So it may be helpful to draw a midline in here. And again, it's just like a really raw sketch, but it's kind of helpful sometimes to see a visual. So we know that the midline like definitely cuts the graph in half. So if it cuts the graph in half and the total height is 10, then the distance from the like midline up to the maximum, the highest point, that must be 5. And then down to the lowest point, that must be 5 as well, because if it's cutting in half, it has to be the same on top and bottom as far as the distances to the two extreme points. And those distances from the midline up or from the midline down, that's the amplitude. So the amplitude is equal to 5. So to write an equation that has that could represent cosine with a height of 10, we just have to write any equation that has an amplitude A of 5. So we don't need to worry about frequency. We don't need to worry about midline. It could be those can be as simple or as like complicated as you want them to be. I'm just going to put in our A is 5. So it'll be y equals 5 goes in for the amplitude cosine of x. And then same thing, I'm not going to worry about b, I'm not going to worry about k. Like I said before, for a problem like this in Canvas, you'll be given kind of a list of functions, and you want to identify, in this case, which one has the amplitude of 5, because the amplitude of 5 is going to result in a height of 10, because the height is going to be double the amplitude. So just a kind of like quick little note, height is always double the amplitude because the amplitude is only kind of like halfway across the wave, or the amplitude is going to be like half the height. So if the height is 10, the amplitude is 5. If the height was like 20, the amplitude would be 10 and so on. So moving on to example 4 says write an equation that could represent a sine wave that has a cycle that begins at a height of 9. So this like wording is very similar to example 3 because they both say like one says height of 10, one says height of 9. But one thing that example 4 has that example 3 doesn't is it's saying that it's a sine wave that begins at a height of 9. And one of the things that is so crucial to remember about a sine wave, and I'm going to go up to the parent function for this, is that sine always starts at the midline. So them going down here, this combination of them saying a sine wave that begins at 9 is just kind of a more complicated way of saying that the midline is 9. So in the general form for a sine function, it's y equals a times sine of bx and then plus k. In this formula, k is the midline. So the only thing that we need to make sure that it's true about our equation is that we put a 9 in for k. A can be whatever, B can be whatever, but to ensure that like our equation represents a sine wave that begins at 9, we got to make sure there's a midline at 9. So it'll be y equals I'm just going to leave a as 1, so sine, and then x, I'll leave b as 1 as well, and then plus k, that'll be plus 9. Okay, so I know I've said it a few times, but like I said, for a problem like this, you'll be given a list of a bunch of different functions or equations in Canvas. And for like this one, for example, you'd have to identify all of the ones that have a midline or a k value of 9 or a 9 that's added to the end of the function. Okay, 19.2 is problem solving from contextual situations. So we just have one problem in this section, but it's a little bit longer. So example 1, Kareem is pedaling his bicycle. Once he reaches a constant speed with the the distance of the right pedal from the ground in inches can be represented by the function y equals 6 sine of 45x plus 14, where x is the time in minutes. Okay, so if we kind of picture, like if you're riding a bike, the pedal moves in a circle. So I'm going to try to create little visual to help make things like make a little bit more sense. These problems are always a little tricky. But so he's pedaling, he's going, it would be like clockwise. But the like kind of way that it's rotating doesn't matter a whole lot, but just so you can kind of picture a pedal going in your head. And then the function itself, it says once he reaches a constant speed, the distance of the right pedal from the ground can be represented by this sine function. So one thing that we know about sine functions is that they start at the midline or the middle. So if these like kind of different parts around the circle represent different heights, there's two middles. So there's like this middle height and this middle height. So I kind of want to narrow it down like a little bit between those two. So I'm going to go back up to the sine function up here. So it starts at the midline. After it starts at the midline, it goes to its highest point next. It goes up to its maximum. So if we're looking at like kind of where we're going after our starting point, if we start on the right, that would go down to its like lowest point on that revolution, versus if we start on the left, then it's going to go up to its highest point on that kind of like circular motion that the pedal's going through. So I'm going to think of that as my starting point. This is the point where he is hitting his constant speed for the first time. So he's reaching his constant speed at that point. And then I want to take this kind of like circle that the pedal's moving in and draw a little like sketch of a graph off of it. So it'll just be a sine graph. So it's going to start, I'm going to draw a midline. I'm not going to worry about labeling really anything yet. Okay, so he starts right here at his midline, and then he goes up to its highest point on like as far as how high the pedal can reach, and then goes back down to the midline right there, and then goes down to his lowest point right here. And then I didn't draw long enough, but he goes back up to his midline to kind of finish like one full revolution. Okay, so I just want to kind of translate like the movement around the circle to our graph, because these are like kind of one of the biggest things that we can pull from this whole unit. So he starts at the midline and goes up. That's this section. The height goes up on the graph. And then he goes from the maximum back down to the midline. That's this section. And then he goes from the midline, the middle height, down to the lowest point. And then he goes from the lowest point back up to that middle height. So that's this section. So we kind of just took that like circular movement that the pedal goes in and translated it to like a graph that's changing over time. So it moves like this. And then now we can kind of use this as a visual to help us answer these 4 questions. Okay, so number 1, how far from the ground is Kareem's right pedal at the exact moment he reaches his constant speed? So we know that that is this moment right here. It's also the starting point on our graph, which I know we don't have any numbers on our graph yet, but we do know this point because we can find the midline from the function, and that point is on the midline. So when you're looking at a function, the midline is the number that's added to the end. It's at like plus k, so that's our midline. So since there's a plus 14 there, that means that this would be y equals 14. And it means that that point, the one that's circled, this guy right here, has a height of 14 because it's on that midline at y equals 14. So for how far from the ground is Kareem's right pedal, you could say 14 inches. And then I'm going to add a little note that that came from the midline because that point began there and we could find that height from the function. Okay, so for number 2, I'm actually going to go back because we're going to kind of, for 1, 2, and 3, we'll be looking at different points on the graph. So I'm going to label them so it's a little bit easier to go back and to kind of refer to those points later on, like if you're studying back over your notes. So number 1 is that initial point right there. And then number 2, it says, what is the greatest distance of the pedal from the ground? So you have to picture that, like, you know, the ground is down here underneath that, like, kind of pedal that he's moving around in a circle because you don't want the pedal to hit the ground. So if we're looking for the greatest distance from the pedal, or of the pedal from the ground, we're looking for the highest point on the graph, which is right there. So this is the point that we need for number 2. We know that the midline is 14, but this point's above the midline. And if we want to figure out how far it is above the midline, we have to look at what the amplitude is, and we can find that from the function. It's the number out in front. So that 6 out in front, that's the amplitude. And that means that that's the distance from the midline up to the highest point. So to find that point, we would just have to take the midline, 14, and then add the amplitude, which is 6. And so that'll give us a height of 20 inches. And that's also giving us our maximum. Okay, so this was the midline. Our setup was the midline plus the amplitude to get our maximum, or the greatest distance that the pedal is away from the ground. And then number 3, what is the smallest distance of the pedal from the ground? So now we're looking at, okay, which point is like the closest to the ground? Remember, the ground is right here. So the point that is the closest is, actually I'm going to grab another color. The point that is the closest is this one right here. It's the furthest kind of down point, or like the minimum. So again, we have the midline. We can find the minimum if we combine the midline and the amplitude, because the minimum is just going to be the amplitude below the midline. So it's going to be 6 below the midline. So this time, instead of doing 14 plus 6, we'll do 14 minus 6. So we'll do the midline minus the amplitude. So 14 minus 6 is 8. So 8 inches is going to be the smallest distance of the pedal from the ground, and that's our minimum. And then one more time, the setup is just midline minus the amplitude to find the midline. Okay, and then number 4, what is the diameter of the circle made by the pedal? So I think this one is almost kind of easier to use our circular picture first to make a little bit of sense of it. So the diameter, we know the pedal is moving in a circle. The diameter is the distance across the circle through the center. So it'd be this distance. Hold on, I'm going to grab a different color because I'm running out. It'd be this distance right here. So through the center and all the way across the circle, that's the diameter. So we can take that, if we can figure out from the circle, that's fine. If you can't figure out the circle, it's just the distance from the highest point on the graph down to the lowest point on the graph. So you can either subtract the maximum and the minimum. That's one way. I'm going to show kind of both ways. I'll just bullet point them here. So you can do the max minus the minimum to find it, which is 20 minus 8. So 12 inches. Or to find the height of this circle, you can go back and use this formula that we talked about up here, where the height is 2 times the amplitude. So you can use height equals 2 times the amplitude, So it'd be the height is equal to 2 times the amplitude. We figured out the amplitude was 6 because it's like that's the 6 that's out in front of the function. So 2 times 6 is 12. And to get the same answer either way, there's just a few different ways to look at it. You can really just go with like whichever way sticks in your head the most and kind of makes the most sense to you. That's the method that you should use. So amplitude, or not amplitude, but the like height of the circle is the distance from the top to the bottom of the wave, or it's 2 times the amplitude. Same answer either way. So our diameter of the circle ends up being 12 inches.